So just a bit of a reminder about the differences between airborne and impact sound. So with airborne sound, a higher test value equates to a better insulation between the rooms or whatever it is that you're measuring. The single figure rating for site test is a DNTW term, and to add to the confusion, you have a different term for if it's a lab test, and that is the RW term. So the W subscript means that it's a single figure for that A-weighted reference curve. The NT is that it's been adjusted for the reverberation time, standardized reverberation times. We don't have that with the lab test because actually the lab facility will have been adjusted, with baffles and acoustic hangings within the spaces, so that they have got a reverberation time of that half a second for their laboratory. And then impact sound, remembering that a lower test value actually equates to better insulation. And the single figure ratings for the site test is LNTW, so similar to the airborne sound. We've got an L instead of a D because we've got a noise level instead of a noise difference, and the single figure rating for the lab test is LNW. So as you can see, it's quite a few different terms and measures that you'll see on different test reports and that sort of thing, depending on how the things have been measured and what type of sound they're for. As well as all of that, we need to think about how sound might physically travel from one space to the next. Obviously, the obvious one is a direct transmission through the separating element, so that solid line straight through the separating wall in this image, and that's what we call direct transmission. But you can also have various flanking transmission paths, and that's where sound may travel through different elements of the construction into the source or into the receiving room. So not directly through the separating element. Some of that path may involve the separating element, but it will involve also other parts of the structure. So it's all very well having a very good separating element construction, but if the rest of the construction is sort of weak acoustically, then sound will travel obviously by the easiest route and still get into that receiving room, even if you've got a very highly achieving separating element. So obviously it's important that with our acoustic detailing, both transmission methods are considered and controlled. And some of the main ways in which acoustic insulation is provided, well, the first one is by providing mass to separating elements and the rest of the construction. So if you've got a thick, heavy construction, then sound finds that very difficult or that performs very well at insulating sound. Something else which enables good sound insulation is actually the isolation of separate layers. So not just having a solid mass, but having separate layers of different densities. That's very good at insulating sound. And then, of course, making sure that any gaps or junctions are well sealed, making sure that there's no sort of very easy paths for sound to travel from one part of the building to the next. So this slide demonstrates both the mass and isolation and how they help to achieve sound insulation. So if we look at the figure, that first image, that first drawing is meant to represent one layer of plasterboard, or sort of sound insulating plasterboard. So that might give you something like 25 decibels of sound insulation. The mass law for acoustics means that approximately, if you double the mass, you can get a 5 decibel increase in the sound insulation. So if we double that layer of plasterboard to 2 layers of plasterboard, we can expect to get about 30 decibels of sound insulation. And then if we doubled that up to 4 layers of plasterboard, all next to each other with no gaps, we might expect to get about 35 decibels of sound insulation. That case isn't shown on the slide. However, if we provide some isolation between the layers and actually have a cavity, as you might have with a light steel frame separating wall, so we've got some cold formed lipped C-section steel studs with plasterboard attached, 2 layers on each side, with some insulation material in there to prevent too much reverberation within that cavity. Then we can expect to get around 60 decibels of sound insulation. So we can see that adding that cavity with a bit of insulation really does improve the acoustic insulation. Obviously, it has increased the thickness of that wall, but it's much better than having sort of 4 layers of plasterboard all together. So mass on its own is useful, but mass separated with isolated layers is even better. And then the third point that I had on the 2 slides previously was about sealing. So that's all about junctions, excuse me, and making sure that there's no sound air gaps, obviously, using acoustic sealant, acoustic filler and filler materials between hard surfaces, so sort of where a wallboard may meet the floor. You'd want to try and keep that junction sort of soft, so you don't have hard surfaces in contact, and that can be done with acoustic sealant or special foam strips and that sort of thing. You also want to make sure that you've got good sort of construction practice. Something that's caused poor acoustics in the past is a build-up of mortar on wall ties between leaves of masonry. So if you get lots of mortar build-up on the wall ties there, or the brick ties, then that reduces the amount of sound insulation that you can get between two leaves of masonry in that case.